So all of that out the way, you'll be pleased to know this is the final section of the lecture for today. This is the final set of new concepts we're going to go through, and then you're just free to go and practice some of the regression stuff that we're going to go through now, or to, as I say, carry on playing around with the classification models that we've been working on so far today. So regression modeling. What happens if instead of predicting whether someone has a disease or doesn't have a disease, for example, or does receive clot-busting treatment, doesn't receive clot-busting treatment, what happens if I want to predict something numerical from my data set instead? So there's a lot of examples of this in healthcare type environments and policing social care. The likely length of stay of someone in hospital based on their clinical features, their demographic features. We have huge amounts of information about historical lengths of stay, etc. How many contacts someone might need within a healthcare service. In a lot of sort of more community-based services, it's not necessarily immediately set how many contacts someone will have with a service. So instead, what you'll find is people will have a certain, they'll turn up, they may have one appointment, they may have 10, they may have 100. Planning services around that can be very tricky. Estimating the cost of patient care or social care packages in the next year, we have a lot of historical data around this. Is there something within this data that can help us to make predictions about people that could be high cost? And then it's so easy to start tripping into the ethical issues of AI. Every time you come up with a good use case, you trip into that problem of, oh, if I notice these people are highly likely to need high intensity of care, then I can do something about it. Well, who are you then not doing something about? Who is missing out because of what your algorithm has predicted? But can you amalgamate these predictions into high-level predictions? Can this help inform your budgeting for the next year? Can it help inform your resourcing in your department, based on the predicted number of contacts that people might need? Can it help you to inform your bed management, that kind of thing based on the models? A bit like Zella's example, where rather than predicting directly or intervening directly with individual patients, it was used to help inform resourcing and planning instead. So there's different ways you can use AI models without tripping into the big ethical problems, but all worth noting. But numerical data, there is value in being able to predict numerical values from machine learning algorithms. So we call this a regression problem when we're trying to make a machine learning problem learn this numerical pattern of data. You'll be pleased to know that XGBoost can do it, decision trees can do it, random forest can do it, and very little has to change about the fundamental model training code once again. So what we're doing is trying to predict some sort of numerical target, and this blue line is showing the output of our model across a different series of data values. And you can see in this case, it's sort of predicting fairly well. It's not predicted it's not made a curve, it's not made a straight line. It's sort of got it's got an output that sort of tracks roughly the pattern of data we're seeing. Now, just like before, you can find that your models can overfit. If we set a decision tree with a max depth of 2 and train it on this data set, then you can see it misses out on this kind of upper peak. It's not perfectly tracking, but it's giving a reasonably good approximation of the real data set. Now, if we set a max depth of 5 in contrast, it's very highly influenced by these outliers that we're seeing, these low values, these very high values that are not really representative of the main pattern of the data. So again, all of these techniques all of these concepts of machine learning model optimization that we've been talking about today still apply when you go to a regression problem. You'll still want to try and avoid overfitting to your data. You don't want it predicting those weird outliers that don't really represent the true reality. Now, regression with decision trees, very simple. Again, from sklearn-tree, we import decision tree regressor. That is the main difference. We have decision tree regressor, and we train the model using our training sets. Now, in this case, I've got a data set of diabetes data. And what I'm trying to predict is an actual, a sort of measurement of diabetic function of some kind. So it's a numerical value, it's a continuous numerical value. And what I've done is train the model just as before. The only difference is that my outcome column, my Y, instead of being a series of classes of, died, survived, etc., something like that, it's just a numerical value. And then we can make predictions in the same way as before. We're still making a predicted outcome. We are predicted using our regressor, and we are predicting from our test data set. And instead of predicting probabilities or classes, classes with underlying probabilities with a likelihood of, how sure we are about this prediction, instead we are predicting numbers for each individual patient. Exactly the same with XGBoost. Instead of importing XGB classifier, we import XGB regressor. The biggest difference, I would say, in how the regression problems are done is how we measure the performance of the model. Things like accuracy and precision and recall don't really make sense in the same way for regression models. Instead, we are using a range of aggregate metrics related to how wrong each prediction is. So let's imagine we've got a model that's trying to predict some value, and the true value for that individual patient is 12. The model predicts 14. That probably isn't too far out. That sounds fairly good. It's out by 2. Obviously, if the actual value is 12 and the model predicts 45, that's definitively worse. It's a bigger magnitude of the prediction being out, the difference between the true value and the predicted value. But it can be a little bit difficult to say whether an error is wrong enough to be a problem. So for example, that first model, if the measure only ever ranges between 11 and 15, and we've predicted 14 and the actual value was 12, in terms of the magnitude of the error within the possible boundaries of it, that's quite a big error. That's still quite a long way out. Is that model going to be operationally useful if it is predicting that incorrectly? And how can we start to tease out those aspects of the model, the model's performance? So we've got a couple of different options available to us. Now, all of these, when I go through them, these are all easily calculated again within sklearn. There are functions that allow you to calculate these, so you don't have to worry about the details of exactly how to calculate them. It's more important to just roughly understand what they are calculating and why that's useful. So the mean absolute error, MAE, is usually what you'll see it referred to as. This works out all of the errors. So for every single prediction that the model has made, it looks at the difference between the prediction and the real value. It then gets the absolute value of the error. So all this means if the error, if the model predicted 15 and the actual value was 11, then it's out by -4. If the model predicted 15 and the actual value was 19, it's out by 4. So you can see that those two would actually cancel each other out if you just added them all together. So instead, what we do is when we get the absolute value of the error, every time there's a negative, we make it positive. Every time we have a positive, we keep it positive. We add all of these absolute errors together and we divide by the total number of predictions. And this will just give us a sense of how big the gap between reality and predictions are. Lower is better. Now, the mean absolute percentage error is the same as the mean absolute error, but it's as a percentage of the total error. So what we do is we divide each error by the actual value. We multiply it by 100. We sum these before dividing by the number of data points. I seem to have not finished that slide there, but effectively it gives us a sense of how big the gap between reality and the predictions are, and it's a little bit easier to compare across data sets. So here, for example, if you were trying to compare the performance of a model, so if you've trained 10 different models and you want to see how they compare to each other, the mean absolute error will give you a good sense of different, of performance. Mean absolute percentage error, if you had a couple of different data sets and you were trying to kind of get a general sense of how far out it was, mean absolute percentage error would be better in a way. There are some really significant drawbacks and limitations to mean absolute percentage error. Sometimes it just inflates, it doesn't really make sense. So just use it with a little bit of caution, but just be aware that mean absolute percentage error is something that you can calculate with these models. There is also the root mean squared error. Here you work out the square of all of the errors, and that's the difference between the prediction and the real value. So again, if we had a predicted value of 15 and the actual value was 11, the error is out by -4. If you have real value 15, predicted value 19, we're out by 4. But instead this time of just going, oh, okay, turn the -4 into a 4, we are squaring it. We are multiplying it by itself. So -4 times -4 becomes 16. 4 times 4 becomes 16. Then we divide by the total number of predictions, and we take the square root of this result. So if we have, 36, the square root of that is 6. 6 times 6, 36, work in the other direction. It's another way to get a sense, again, of how big the gap between reality and predictions are. But the good thing about RMSE, root mean squared error, is that it's more sensitive to outliers, the extreme points, than your mean absolute error, which is a very good thing if your very wrong points are more important to you than slightly wrong points. So if that's the case for your particular prediction model, then root mean squared error may be a better choice. Finally, we've got R squared, which is also called the coefficient of determination. This is roughly the proportion of the variation in the dependent variable, the thing we're trying to predict, that is predictable from the independent variables, the features we're feeding in. Higher is better in this case, and it can be a maximum of 1. Now, this is a really, again, useful measure of, sort of roughly comparing how useful is your model? Is there actually much predictive power to it? Is there, from the data set, the data points you've been able to provide, does that actually give you much detail? But also it can be a great way of comparing, if you run multiple models again, is it, the closer you get your R squared to 1, the better. Now, R squared can be sort of manipulated a little bit. Sometimes it gets inflated just by adding more and more features, even if those features don't actually help the predictive power. Now, like I say, you don't have to worry about the details of how to calculate those. sklearn can do this for you. So from sklearn.metrics, we can import mean absolute error, mean absolute percentage error, R squared, and root mean squared error. Now, again, a bit like I was talking about at the beginning of this section, there is a very good chance that you might want to call your outputs exactly that, and that could cause problems because you're overwriting the variables. So don't do that, but do calculate your mean absolute error, your MAPE, your root mean squared error, and R squared score. These aren't the only ones available as well. There are additional metrics out there that you may be interested in looking up if you do go on to do a regression model as part of your project, but these are a couple of good ones to get you started with. What you can also do to evaluate the model is start to do things like predicting the actual values versus the predicted values. So in this case, we read along to the true values and we read up to the predicted values. Here we predicted the true value was 100, but we only predicted about 75. Here, the true value is, let's say, roughly 250 on that one. We only predicted 150, but if I read up to this one, in this case, the true value was about 240, let's say, and we predicted a bit closer to what it is. This straight line indicates, a perfect prediction. The closer these points cluster around that line, the tighter the fit of those points around that line, the better your model is performing. The other thing you can do is calculate the residuals. And the residuals are just the error, the gap between the predicted value and the actual value. Now, what is useful about plotting these residuals as a histogram like that? So here you can see that a residual of between about 0 and minus, let's say -10, just for the sake of argument. We've got 8 instances in our testing data set where that happened. Residual of 0 to roughly +10, we've got roughly 5 instances where that happened. So, and this red line here is just showing an error of 0. Now, you want them closely clustered around 0, that's better. But what you also ideally want them to be is fairly symmetrical. You want to see this plot kind of rising up to a peak in the middle and dropping off again. The more symmetrical it is, the more that is suggesting your model is it's not always under predicting, it's not always over predicting, it's performing well across, it's performing well across the whole data, or it's at least performing badly consistently across the data set. Now, other good news, like GBM, Cat Boost, sklearn, the histogram gradient boost, you can classify within that, etc. Add a boost, random forest, etc. They can all do regression modeling. I've just shown here the different things you need to import, and the main thing you do is just change the word classifier to regressor, and then everything else carries on as per normal. You could also consider multiple linear regression. You will need to scale data when you're doing this, a bit like in logistic regression. And linear regression traditionally, if you're coming from a statistical background, a statistical standpoint, has assumptions. It has assumptions about how the relationships in the data are, and various things like that. There's a school of thought from machine learning that doesn't matter as long as the predictive power is good, but I would still err on the side of caution there. It's quite a divisive topic, and I would say, just be aware that linear regression, so just kind of fitting a straight line to your data, is definitely an option. And multiple linear regression just means you're providing multiple, more factors for it to consider and build your regression model from. sklearn can do that, but just kind of be aware of maybe some of the kind of bad, well, yeah, it maybe just be aware it's an option, but for today we'll just stick with XGBoost, etc. Decision trees, because it does a very good job. And just like with the classification models, it does a very good job in general of making these predictions. You can always start to combine as well with other elements of your data. You will start to build additional features up above and beyond what already exists in your data potentially. We talk a lot more about this in the final session, but let's even bring in some of the stuff that we talked about in previous sessions in the geographic modeling stuff. You could start to combine with geographical elements because everything is related to everything else. Near things are more related than distant things. So geography can start to be a feature in your models. This doesn't just apply to regression, this is true of classification models as well. For example, if you were predicting house prices, you can start to add in features like how close is it to a park, how close is it to town, that sort of stuff, that you build up all these features from geographical elements. So I am going to now go on to a brief chat about data preparation. Now, I've talked multiple times throughout today about OneHot data encoding. You'll be pleased to know that I'm finally going to actually show some examples, some visual examples of what that means and how you can do it to your own data sets, which gives you a lot more freedom to go and find any data set on the internet that you might want to try out and play around with. And there will be a data set, you will be able to turn that data set into something that works with machine learning algorithms, with all the ones we've been working today. So the Titanic and Stroke datasets we've worked with so far have already been pre-processed to make them suitable for the algorithms we've been using. And a big part of this is what's called OneHot encoding. So this is taking something like our cabin letters. So if we know that we've got a cabin letter of C, a cabin letter of E, and we've got all these different passengers, instead of having this categorical column, we sort of pivot it out. Instead of having one column for representing this data set, we have as many columns as there are different unique categories. So in this case, we can have something like cabin letter A. Well, no one in this data set we're looking at here had a cabin letter of A, so all of those are zeros. Cabin letter of B, nope, still no one there, zeros. Now, passenger 2 had a cabin letter of C, so we put a 1 in this column. And we can see, looking across passenger 2, they only have a 1 in one single column. All the rest are zeros. And so on and so forth. And we can also have something like a column for cabin letter missing, because that's useful data in its own right sometimes. It's not too difficult to do this in your own data sets. There is a method available for it in sklearn, but I personally find it easier to do it via a method in pandas. So let's return to that data set we had of my music taste from earlier and take a look at the genre column. So you'll be sick of me saying the words rock, pop, and musical, but OneHot encoding is going to spread out our single genre column into as many columns as there are categories. And it's going to put a 0 in the matching category. Sorry, it's going to put a 1 when that is exactly what it is. So Salt is a Swing, rock song, Genie in a Bottle is pop, Room Where It Happens is from a musical, and so on and so forth. And we've got zeros in all of the other columns. We can use what's called the get dummies function in pandas to do this. So if I apply the pandas get dummies function to data, and in here the column I'm interested in, so this is my data frame, this is the column I'm interested in, genre. Now, what we're getting when we create this OneHot object is this over here. We are creating a new data frame. The indices align with the existing data frame, but instead of having that one genre column now, we have a series of trues and falses. From our original data set, we can now drop this column, the original column, because we don't need it anymore. It's over here, it's encoded in this OneHot object. So we get rid of it, and then we join this new OneHot object, this new data frame, back to our original data set. The other thing that's worth noting there is we use the index to join the two. Now, in this case, we can join it just using this notation. It will automatically use the index, but it's just worth knowing that's what it's joining on, the row numbers effectively of the data set. So, other thing that's worth noting is in Python, in a lot of programming languages, true and false are always considered to be equivalent to 1 and 0 respectively. 1 is true, 0 is false. What this means is we don't have to explicitly change the columns from the Boolean, the true, false, to a float or an integer, because the algorithms can generally kind of cope with that. They understand that, that sort of transition. But we can do it if we want to. If we would rather convert it, we can create our get dummies, just like we were doing here, but we just do dot as type integer, and it will turn all of these into zeros and ones instead of a series of false and trues. The other thing that's worth noting about the get dummies is sometimes the resulting column names may not be very descriptive. There is an argument you can use called prefix that will add a string to the start of each resulting column name. So here, instead of just, if we add prefix equals genre, these would be genre house, genre musical, genre pop, genre rock. That can be very useful for certain data sets. So actually, if we go back to our cabin letters, for example, that's how we would have got cabin letter underscore A, cabin letter underscore B, rather than just A, B, C, D, because without the additional context, what on earth is A, B, C, D referring to as a column name? Now, for categories where only 2 options are present, we can also choose a simpler option. So if we don't have a data, so in a lot of data sets, we might have a column called something like male, where 0 is equal to female and 1 is equal to male, or vice versa, with a column called female, 0 is male, 1 is female, that sort of thing. But we may also have some data in our columns that are, for example, a category called age group that just has the values of child or adult. So instead of OneHot encoding these, we can keep it as a single column, but we might need to change what is stored in it. So in this case, you might want to, you can have gender categories that may be only, or sex categories that only provide a binary option. That can be quite common, and that's what's done in the Titanic data set. But there are a couple of ways we can go about this in Python, and here's one of them. So here we would do data age group. If we have a column called age group in a data frame called data, we would replace all the values of child with 0. And we're saying, please overwrite this existing column. That's what the in place is doing here. And then we go through and say for the age group column, now go through and replace every instance of adult with a 1, and in place is true. Now we can either store what we've done in some sort of accompanying data dictionary or within our notebook, so it's very clear what that means. What, age group isn't necessarily that descriptive. You might not understand that 0 is child, adult is 1. You might also want to consider renaming the column. You might want to look up how to do that in pandas. So actually we might want to call that column is adult, and therefore 0 makes more logical sense to be a child, 1 makes more logical sense to be an adult in a column called is adult. So we're going to cover a bit more about data prep in later sessions. So OneHot encoding and dealing with those kind of dichotomous variables, the ones with 2 possible values, are the key ones for the last exercise of today. But down the line, it will be important to think about how can we best deal with missing data points? Is it using the built-in features, or is it something else like mean imputation or median imputation, or even a more complicated version like another machine learning model? How do we deal best with highly correlated features, those features that sort of increase in some or decrease in some relationship with each other? That can cause problems within machine learning algorithms. Inconsistent data, how do we tidy that sort of thing up? If you've got a category like, contact, How do we start to tidy up things like variation in email, e-mail, and email with a capital E within one data set, so that we're not kind of artificially adding our own variation into it when there isn't any. Irrelevant data, outliers, reducing the number of dimensions. So if you've got, 1,000 different columns of data, that's probably not a good thing in a lot of cases, and there's various ways you can deal with that better. And feature engineering, creating additional features from data that exists that allows machine learning models to work better. Now, to be honest, the data quality in the prep can have more impact than almost anything else, more impact than tweaking all these hyperparameters like we've been doing. Garbage in, garbage out. Your data quality and your data prep matters more than anything else, and it will probably take a lot more of the project time than you would ever think. 90%, 80 to 90% of most data science is prep and tidying. Well, I want to say that's an overestimate, but to be honest, it's probably not. It's a lot of what you will be doing. It's a very, very crucial part. So I'm just going to quickly check the questions before we go on to talking about what the final exercise of today will be. Dan, any questions that you want to highlight?
I think everything that's come up has been answered in the chat, I believe. I can't see anything else, but please shout if people have said something that I've missed.
Brilliant. I have also been scrolling just as you've been saying it, and I also can't see anything that hasn't already been answered. So thank you very much to everyone who's answering those questions. Right, final thing, a little bit of a chat about the next exercise. And we are going to be working with a hospital length of stay data set. It's a nice training data set that has been created by Microsoft. Unfortunately, sorry, we seem to be mentioning their name a lot today. This is a regression problem where you're trying to predict the likely length of stay for patients. Now, this data set is going to require a little bit of pre-processing before you can use it. We're going to take a look at the columns that we've got available. So we have a unique ID of the hospital admission. Think about whether that's something that's useful. Do you actually want to keep that in there? Do you also want to keep the visit date in there? Is that something that you want to be predicting from? We have the R count, which is the number of times that people have been readmitted within the last 180 days. So if they've come into hospital before, and if they have come into hospital before, how many times have they come in before? We've got gender, which is just the gender of the patient. In this particular instance, there are only 2 categories provided. We've got the a range of variables relating to diseases or conditions that these people already have. So what we have for each of these is a 0 or a 1. That's all that's available. So they either have dialysis renal disease or they don't. So if they don't, it's a 0. If they do, if it's a 1. They either have depression or they don't. If they don't, it's 0. If they do, it's a 1, and so on and so forth. And that's all of these columns. We then have a series of float values. These are the average values during the encounter. These are all on different varying ranges. They aren't kind of bounded between any particular bounds that's consistent across them. We have an integer that indicates how many additional diagnoses they have outside of what we had available here. We also have a facility ID. Now, these facilities are basically where were they when they were staying in the hospital, which facility are they staying in? And these are A, B, C, D, or E. And the final thing is the length of stay. That's our column, and that's what we want to predict. And these are always integers. Now, when you're going through this data set, when we open it up in a minute, or after you've had a bit more playing time with the other data set, if you want to do that first, if you want to carry on with your classification exercise, what you will need to do is consider how to deal with the number of readmissions in the last 180 days. These are stored as a string. You're going to want to consider how to deal with the string which is storing the gender of the patient. You're going to want to consider what columns you might want to drop. You're going to consider what to do with things like the facility ID, which again is another categorical variable. So just look back through the slides where we've been talking about data processing and have a think about how you would deal with that. When you're playing around with this data set, and to be honest, as you've been playing around earlier today as well with the classification stuff, you probably find yourself wishing you could do quite a few things. Automating the process of working out the best hyperparameters, you've probably found that to be quite tedious. Well, great news is in session 4J, we will tell you exactly how to automate that process. You will gain a better idea, you want to gain a better idea of why on earth is your model making the predictions it is. You'll want to peel back the curtain and see what is going on behind the scenes, what factors seem to be important in the model making its predictions. How does that vary for individuals? Is it always the same? Is it a different factors more important? How do they actually influence the final prediction? All of that's covered next week in session 4G. And you might even want more models or more ways of combining models. Can you make it even better? We'll cover this in session 4J. So we've got a notebook called Regression Tree Exercise. That's going to help you be guided through the initial data cleaning steps of the data set, but after that, it's up to you. You're just trying to build the best performing model to predict the length of stay from the available data set. One thing I'd also mention is in this data set, there's various columns that say something like flag for during encounter. For the purposes of today, we're going to assume that this is all data that's available at the very point that, you know, when people are first rocking up to the place they're going to be staying, the hospital they're going to be staying in. We're going to assume all of this data is available. When you get to real world models, you really need to think about, is this data going to be available when I want to predict? You don't want to put something in if it's not going to be. But here, let's assume that all this data is available from the very beginning. So we're trying to build a model to predict the length of stay from the available data set. I want you to try out a decision tree regressor, and I want you to try out at least one type of gradient boosted regressor, and I want you to calculate at least one metric for each. So maybe mean it, absolute error, maybe RMSE, you know, take your pick, and then start building, start adding more in. But though that's the kind of ideally where I'd like you to get to. You're going to want to explore documentation and additional resources to find out more about the hyperparameters you can tune. And we're just going to work on this now until the end of the day. So you've got just over an hour. The other thing I'm going to quickly mention is that there is a series of additional slides at the end of today's lecture notes with a load of extra videos that just go into a bit more mathematical detail about gradient boosted trees and all the variations of gradient boosted trees if you are interested in that area. But final question that's come up, is there a way to use something similar to dichotomous columns to use conditional logic? So e.g. if age under 18 then true. Yep, there are ways to do this within pandas, so you could create some sort of column based on a condition like that. That is trying to think if I've got an example in there. I don't think I do, but I will share an example of how you could do that within the class Tannoy at some point, because you could definitely have a play around with trying to do that sort of thing as well in today's exercise. So, right, I'm gonna stop sharing. I'm gonna open up the breakout rooms. I will leave you within your groups to decide whether you'd had enough of that previous exercise or if you want to carry on with that for a little while first. And then, yeah, have a play around with these data sets, and I will be going around seeing how you're getting on. So thank you very much for listening. I hope you found today useful. I hope you've kind of enjoyed seeing all the different models that are available to you and just how you can start to explore and explore all of what machine learning can offer to you. So right, with that, let's open the rooms up. I will see you in your rooms.